All right, we're going to finish up this chapter, and we're starting with antibiotic resistance. So, and this could be resistance to an antibiotic, or it could be resistance to a synthetic or chemosynthetic agent. Or this antibiotic resistance is the ability of the microorganism to resist the drug. It's found a way to change its target so that it is not affected by the drug. There's no place for the drug to attach to. Or maybe the organism has found a way to block the drug from coming through the cell wall and the cell membrane. Or maybe it makes a chemical, an enzyme, that inactivates the drug before the drug can do any damage. Whatever mechanism, that's drug resistance. It is not resistance of the host to the drug. This is purely resistance of the bacterium or the microorganism. Protozoa can be resistant to drugs. Viruses can be not affected by drugs, but mainly we're talking bacterial resistance. There's an excellent website as the CDC on their A to Z list of topics. If you click on D and go to drug resistance, you'll find a wealth of information. This is a big problem. I'm sure you know that. It's a problem in hospitals and clinics and nursing homes and things like that, where the infections are called nosocomial infections, that is, hospital-acquired, or usually it's used to describe healthcare-related infections. But also there's a lot of drug resistance involving microorganisms out in the general population, not associated with healthcare. Those are called community-acquired drug-resistant infections. Reasons: overuse or misuse of drugs, both in the way they're prescribed by doctors and pharmacists, and by the way people are taking them, and patients that are non-compliant. That is, they start taking their drugs and they stop after a couple of days. And the bacteria that are causing the infection have not been killed off. Your drug level goes down. The bacteria start regrowing again because there's not enough of the drug to block them. And now you have an infection again. But this time you've got a resistant population to that drug. So here is how it occurs. We've already done genetics, and as you can see, these are things that came up in the genetics chapter. Transformation: free DNA passed from the environment to a cell. It could be a dead cell lying on the ground, free DNA sitting there, cell dead, and another cell comes in contact with the DNA. DNA is taken up into the new cell. The new bacterial cell now gains drug resistance genes via the plasmid or free DNA, is now drug resistant. That's transformation. Transduction: drug resistant genes could have been picked up by a virus. Remember, virus gets into host cell, takes over host cell makes baby viruses leave host cell to go infect more host cells. A virus can be a carrier of drug resistant genes. Conjugation: a couple of bacteria get together, one with drug-resistant genes, one without drug-resistant genes. They sexually reproduce. A plasmid is passed between them. Plasmid might have drug-resistant genes on it. Recipient cell now has drug-resistant genes. Or it could be a random mutation. Or it could be an induced mutation because of UV radiation or whatever. Okay. That's how they develop. So I'm going to talk about this in a little bit more detail in class. Here's a good look at an E. coli culture. It's the same strain of E. coli left and right, except the one on the right has a resistance associated with a plasmid to an antibiotic called tobramycin, and that is tobramycin with a little asterisk on it at about 4 o'clock. So on the left, that strain is sensitive to tobramycin, but on the right, it is resistant to tobramycin. Notice that pretty much it has the same sensitivity to the rest of the drugs that are on the plate, the same other 5 drugs. Okay, I've already gone over this. So as a result of transformation, transduction, mutation, whatever it was, This is how the bacterium changes, the actual application of that genetic change. Okay, so what do you do? What can the medical establishment do? One, give enough dosage of the drug to get rid of the infection and make the patient take it. You've taken antibiotics before, I'm sure. You're told to take it for 10 days or 7 days or 3 days. How often do you think people are taking a drug that is meant for 10 days? Their symptoms go away. By day 5, they just stop taking the drug. They think everything is fine. Combinations of drugs. Instead of using one drug, hit it in 3 different ways, using 3 different targets. That's what they do for HIV. They use a triple drug combination. It's called an HIV cocktail. Give narrow spectrum of activity drugs rather than broad spectrum that could decimate a huge percent of your normal flora and at the same time put extra pressure on bacteria to become drug resistant. Rotate drugs. Take them off the market for a while. Put them back on the market. You're reducing the pressure on bacteria to change, to adapt. Limits on over-the-counter drugs. Development of new classes of drugs by pharmaceutical companies. They don't like to keep developing those things. They'd much rather use drugs they already have instead of putting new ones in the pipeline. It costs way more money for research than using the ones you've got. Reduce antibiotics in feed, animal feed. More than 50% of the antibiotics made in the United States are given to chickens, pigs, cows. That drug resistance that may be in the bacteria of an animal may end up being a problem in a human. And preventative medicine. Interesting ad trying to educate the population about the fact that viruses are not treated with antibiotics. I'm going to skip over the different groups of antibiotics because we're actually going to do something with this in class. I did want to take you through. I'm going to let you look at it. The sulfa drugs. I've already actually talked about some of these in different ways. The penicillins. Here's a good look at about 5 different variations of penicillin. These are semi-synthetics. The cephalithins, aminoglycosides like streptomycin, kanamycin, neomycin, amikacin. The azoles, meconazole, metronidazole, ketoconazole, clotrimazole, very often used for yeast infections, as well as some bacterial infections too. Acyclovir, already mentioned as an antiviral, very important for herpes as well as shingles. The quinolones like Cipro, moxifloxacin, Glevaquin, mentioned how they block the unwinding of supercoiled DNA in bacteria. And of course we haven't really talked about antiprotozoan or anti-helminthic, but they each have their own sorts of drugs that are given. And the last thing I want to mention are problems, limitations. We've talked about some of these already. Drug resistance, I don't think we need to do that anymore. Allergies, we're going to talk much more about in the immune system. Host toxicity, not a problem. Let me jump down to prevention of natural acquired immunity. When your immune system sees an organism and responds against it, that response lasts for years, sometimes a whole lifetime. If you deprive your immune system of identifying, responding to the microorganism that's causing your infection, you're at a disadvantage. Your immune system is better than any antibiotic. Okay, the last thing, I've already mentioned normal flora infections, but let me give you a couple of examples. These are called endogenous infections or normal flora infections. I've got 2 good examples here. Look down here at the bottom. This is a view you don't see often, well, unless you're a gynecologist. You're doing a pelvic exam on a woman. There's a speculum that's inserted in the vagina. This is the vaginal wall you're looking at right here. And that is the bottom of the uterus called the cervix. There's an opening right there. And look at this white kind of cloud-like stuff. That's Candida albicans yeast, your common vaginitis yeast. Why do so many women get yeast infections? Well, one reason is giving antibiotics for urinary tract infections caused by bacteria. You wipe out the competing microorganisms in the vagina, and if the woman has Candida yeast as normal flora, those antibiotics won't do anything for the yeast, against the yeast, or kill it, and now there's all this room for Candida to grow because the other microorganisms have been decimated, populations gone, and all this nice room to spread out in. The view that you're looking at up here, another view you don't see very often unless you're a gastroenterologist. You're looking at a colonoscopy. You're going up the colon. And there's a fecal matter. This is fecal matter. You have to evacuate fecal matter before you go get a colonoscopy or a sigmoidoscopy. Look at the wall of the large intestine and notice these big, angry red lesions. These are inflammations of the wall of the mucosa caused by Clostridium difficile, sometimes called C. diff. Very often you see it just written like that. It's normoflora in everyone. It's normally kept in check by the competing microorganisms. But again, if the person is given antibiotics, particularly long-term, and those antibiotics knock out lots of other bacterial flora in the gut, and Clostridium difficile is not affected by the drug, it will then overgrow, causing colitis. And colitis will cause really bad diarrhea. We're talking really bad diarrhea, not a pleasant thing to consider. Usually always associated with antibiotic therapy. And here's just a look at numbers of colitis, pseudomembranous colitis, associated with antibiotic use over a 5-year period. And particularly notice the age groups that are most susceptible, over 65, the green line and the yellow line. That is it.